And yes, the Steric clash would be a great name for a rock band. Hey ninjas, let's talk stability of Newman projection. As I look at the 4-carbon molecule butane, there is free rotation about the C2-C3 bond. And as we rotate one of these CH3 groups around in a circle while holding the other one constant, we can get a variety of Newman projections for butane. Some are more stable and some are less stable. In this video, we'll learn how to qualitatively and quantitatively determine the stability of all of these various Newman projections. Before we do that, there's a term that we need to know, and that term is steric clash. And yes, the steric clash would be a great name for a rock band. Electron domains don't like to occupy the same volume. Electrons can't take up the same space. So when we have large groups that are trying to occupy the same space, they start to bump into each other. Their electron domains start to collide. They start to have steric clash. The closer those electron domains are to each other in space, the more steric clash, and then we can get them as far apart as possible, and then we can minimize the steric clash between large electron domains. So the degree of steric clash in these various Newman projections is going to be the main driver between how qualitatively and how quantitatively stable these various Newman projections are. We will talk about steric clash a lot throughout the rest of the course. So if you haven't heard about this term yet, you will as you move forward. In terms of Newman projections, there's one molecule whose Newman projection is as stable as it can be. Can you imagine what that molecule might be? That molecule would be the staggered version of ethane. In the staggered version of ethane, every hydrogen is offset from every other hydrogen, and none of those electron domains are starting to occupy the same volume. As far as Newman projections goes, this is as stable as it could ever possibly be. When we quantitatively describe the relative energy of other Newman projections, we do so relative to staggered ethane. We arbitrarily set the relative energy of staggered ethane to 0 kcal per mole, and everything that's less stable than that is higher in energy with a positive energy value. Now, I say relative energy. Staggered ethane doesn't actually have an energy of 0. That would be absolute 0. That's not physically possible. So this is a relative scale. Relative to staggered ethane, everything is less stable, higher in energy than staggered ethane. But how much less stable? Just in this molecule, we could start to make some qualitative guesses. Hydrogens are fairly small. Carbon with 3 hydrogens are a larger group. So if those larger groups start to occupy the same space, qualitatively, that's probably higher in energy. And if they're completely eclipsed with each other, that's probably very bad. But if we can separate those CH3 groups, maybe get them as far apart from each other as possible, that should minimize the energy of this molecule. But how do we quantify those differences? Every time electron domains start to collide in a molecule, every time there's steric clash, there's an energetic penalty associated with that steric clash. The most common Newman projection interactions are listed here. We start with no energetic penalty and we get to a very large energetic penalty when 2 carbon groups are eclipsed. This is by no means an exhaustive list. It doesn't describe what happens when we have heteroatoms or atoms that aren't carbon or hydrogen in the molecule. It also assumes a generic carbon alkyl group. Depending on the length and the steric bulk of that alkyl group, these numbers will be slightly different, but it's usually good enough for first-time sophomore organic chemistry to just stick with these numbers. That will cover most of the bases. We can use these energetic penalties to plot a graph of the relative energy for each of these Newman projections. Very little maths is harmed in the making of organic chemistry. This is about as complicated as the math gets. All we have to do is walk our way around the Newman projection, figure out what kind of orientation we're looking at, and add up the energetic penalties. We will plot these energies with respect to the dihedral angle between the 2 CH3 groups. In this Newman projection, the 2 CH3 groups are eclipsed, and so they will have a 0-degree dihedral angle relative to each other. This should be the highest energy structure of this whole system. It has 1 carbon-carbon eclipsed interaction. If we look on our list, carbon-carbon eclipsed is the highest energy interaction, and it adds 3 kilocalories per mole of energetic penalty. It also has 2 hydrogen-hydrogen eclipsed interactions. Looking at our list, that adds an extra 1 kilocalorie per mole of energetic penalty. In total then, this structure is positive 5 kilocalories per mole energetic penalty relative to staggered ethane. We can add that data point here for the 0 dihedral angle. For this structure here, now the carbons are 60 degrees dihedral angle. This would be like positive 60 degrees, and this one would be like negative 60 degrees dihedral. In this structure, we have a carbon-carbon Gauche interaction. A carbon-carbon Gauche interaction adds 0.9 kilocalories per mole of energetic penalty. The remaining interactions are carbon-hydrogen Gauche and hydrogen-hydrogen Gauche, and if we look at our list, those don't add any energetic penalties. The only penalty in this staggered Newman projection is the carbon-carbon Gauche at 0.9 kilocalories per mole. So for both the positive 60 and the negative 60, we can add a data point at 0.9 kilocalories per mole. In the next staggered Newman projections, now the carbons are 120 degrees dihedral from each other. Here we have 2 carbon-hydrogen eclipsed interactions. Each carbon-hydrogen eclipsed interaction adds 1.3 kilocalories per mole of energetic penalty. It also has 1 hydrogen-hydrogen eclipsed interaction that adds 1 kilocalorie per mole. Adding all those together then gives us 3.6 kilocalories per mole energetic penalty. For both the positive 120 and the negative 120 dihedral angle, we can add a data point at 3.6 kilocalories per mole energetic penalty. Finally, we can look at the 180 degree dihedral angle. The interactions here are carbon-hydrogen Gauche, which is non-penalizing, and hydrogen-hydrogen Gauche, which is also non-penalizing. There are no penalizing interactions in the anti-version of butane. So the relative energy of anti-butane is 0 kilocalories per mole relative to staggered ethane. Now we can connect these data points with a curve. I'm extending these curves off to the right and the left because we could continue rotating the CH3 all the way back around. We notice something very interesting. All of the eclipsed Newman projections are all higher in energy and less stable than all of the staggered Newman projections. This is generally true. Generally, a staggered Newman projection will always be more stable than its eclipsed counterpart. We also see that not all eclipsed Newman projections are equal, and not all staggered Newman projections are equal. Some of the staggered Newman projections are more stable than others. The best Newman projection should be fully staggered with the largest groups as far apart from each other as possible. There are numerous other examples we could do, but this list will get you pretty far with Newman projection stability.
Thanks for training with us today, ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.